in lab to make sure that you know the names of the different molecular shapes. So this is 5 of them. I believe there's a total of, what do we have, 11 names. I listed them on the board when we were doing the lab. This is all based on what's called VSEPR theory. VSEPR stands for valence shell electron pair repulsion. That's what a VSEPR stands for. And remember, a pair of electrons is supposed to be this lobe of repulsion, because you've got one electron going in one direction, you've got the other electron going on in the other direction, and this lobe of repulsion influences the geometry of the molecule, the paired ones as well as the non-paired ones. Remember, the paired electrons have a smaller lobe of repulsion than the non-paired electrons, which have a larger lobe of repulsion. That's what we call this idea of electron domains. So generally when they're asking about electron domains, they're talking about the electron domains around the central molecule. In this case, what's the central molecule, A or B? A. Okay, so we've got a non-paired electron domain there. We've got 2 single bonds, which count as their own electron domain. And then we've got this double bond, which actually counts only as a single electron domain. So if I was looking at just the electron geometry of this molecule, there would be 4 lobes of repulsion. Remember we did the balloons thing? There would be 4 balloons I would use to represent the geometry around the central atom. So if we have 4 electron domains, what do we call that geometry? Tetrahedral. Okay, that's the electron geometry in this particular molecule. But in this molecule, because we have non-bonded pairs around the central atom, the electron geometry and the molecular geometry are different, right? The electron geometry is tetrahedral. What would be the molecular geometry of this? No, not bent. Trigonal pyramidal. It would be that, not the trigonal planar, it would be pyramidal, because that non-bonded pair of electrons here, remember, sort of pushes down the planar part of the molecule. All right, here is some bond angles. This is with the balloon depiction. This is what a linear molecule looks like. If I was going to show you an example of a linear molecule, let's see, where is that? A linear molecule would be something like carbon dioxide, right? It's got double bonds here and here. Because it's got double bonds on each side, each of those double bond areas is considered only a single lobe of repulsion, or only a single electron domain. So if I look at the angle between the oxygens in CO2, that angle is 180 degrees. So that's something that's important when you're talking about molecular geometry. So that's a linear molecule. The next type is trigonal planar. I don't have a molecular model example of that, but a trigonal planar molecule is often those types of molecules that exhibit resonance, right? Like NO3 that we just talked about on the quiz, NO3 with a -1 charge. There's a good trigonal planar molecular geometry, and it's trigonal planar because if we look at the geometry of NO3 minus, right? Here's our NO3 minus. NO3 is NO3 minus. Nitrogen has 5, each oxygen is 6, that's 18, plus 1 more, that means 24 electrons. I put nitrogen in the middle. When I distribute everything, it's going to look like this, right? We've got electrons there that are non-bonded pairs, and they certainly are important, but they're not important to the overall geometry of the middle. Now, this one is tricky, because some people think, oh, there's 1, 2, 3, 4 bonds around that central atom, it's tetrahedral. But that's not the case, because you've got a lobe of electrons here, an area of electron domains, 1 more here and 1 more here. And so what that creates is not only a molecule with resonance, right, because this bond could be there or there, but creates a very planar molecule. It's going to be flat. If I could turn this on its side, it would look very planar as a molecule. And like I said, unfortunately, I don't have a molecular model to show you that represents that. But the bond angle in a trigonal planar molecule is 120 degrees between the component atoms on the outside, the peripheral atoms. The angle between them is 120, and that's important to know. Then we get to tetrahedral electron geometry. Tetrahedral is where you have electron geometry that has 4 lobes or electron domains. Okay, on paper, tetrahedral looks like it's 90 degrees, right? If we were going to draw this molecule, this is CH4. This molecule doesn't look three-dimensional. I would look at this on paper as a 90-degree angle. That is not true. What is actually the angle in this particular? That's 109.5 degrees. And that's super important for you to know, that idea of that particular bond angle. It's not 90 like you would think it is on paper. It's 109.5. All right, we can take that tetrahedral molecular geometry and we can change it slightly. Let's go into here. Here's another good example of changing tetrahedral molecular geometry. NH3 molecule. If I look at the, if I look at the Lewis structure for NH3, there's NH3. 5 and 3 makes 8. I've got N, non-bonded pair of electrons there, and hydrogens all the way around. All right, that non-bonded pair there means that I'm going to take off an atom on this geometry. Now, the electron geometry of this molecule is still tetrahedral, right? So the electron geometry of this one is tetrahedral. And that's because there's 1, 2, 3, 4 electron domains, or 4 lobes of repulsion created by bonded or non-bonded pairs of electrons. And electron geometry takes into account both the bonded as well as the non-bonded pairs in this one. In this case, we would say there are 3 bonded pairs and 1 non-bonded pair. So that's the electron geometry. The molecular geometry of this thing we call trigonal pyramidal. Right, because it's not planar, right? It's not planar. These are not flat. That's not a 120-degree angle there. What actually happens is because this non-bonded pair is actually a larger lobe of repulsion or a larger electron domain, it pushes these angles down a little bit more. And now, since this is a trigonal pyramidal molecular geometry, this angle between the molecules goes down a smidge. It's about 107 degrees now, and that's once again because this non-bonded pair of electrons up here is a larger lobe of repulsion. That's a bigger balloon. Remember, I used a different color balloon, and I said it was supposed to be a larger balloon that we were using up there. And so what happens is it pushes these down a little bit more, from 109 to 107. We can take this same electron geometry, this tetrahedral electron geometry, and we can go one more. We can say, all right, let's look at H2O. H2O also has 8 electrons as valence electrons, but O is in the middle, and then we're going to put the H's here and the H here, and then I'm going to put non-bonded electrons on the top. The Lewis structure is not as symmetrical as it could be. If you're going to draw the Lewis structure and try and make it as symmetrical as you could, right, you would draw something that looks like this, but that wouldn't necessarily be the best representation of what it looks like. If we take this molecule and remove one more of those atoms, now I have 2 areas where there's electrons that are not bonded to anything else. They certainly still influence the geometry of the molecule, right? But now on this one, water's electron geometry, we call it tetrahedral still, right? Because there's 1, 2, 3, 4 areas of electron domains or lobes of repulsion. But the molecular geometry on this thing is called what? Bent, which is very different than what this would look like. That would look like linear, right? You say, oh, that's linear molecular geometry. But in reality, water looks like this, which makes it very, very polar, because now you've got this really negative side of non-bonded electrons sticking up on top of the molecule all by itself. And then you've got this positive part of hydrogens on the bottom, which makes that portion of the molecule very positive. So now what happens is this bond angle goes down even more, because that is a larger lobe, that is a larger lobe. Now it goes from 107 to being about 105.5 or 105.7. I think I've heard it. It goes down a little bit more, because once again, the non-bonded pairs of electrons exhibit a larger lobe of repulsion than the bonded pairs do. And that's important to know, that the geometry and the angle between the bonded atoms changes as the number of bonds decreases. All right, so there's NH3. molecular geometry. And there's good examples that we just went through. Tetrahedral. All three of these molecules, their electron geometry is tetrahedral, right? The first one, the tetrahedral electron geometry, is also the same as the molecular geometry. The second one, tetrahedral electron geometry, here is trigonal pyramidal molecular geometry, and here it's tetrahedral electron and bent molecular geometry. Of these three, which are polar? Of these three molecules? The bent one is definitely super-duper polar. Is there another one that's polar? Trigonal pyramidal is slightly polar. Not as polar as water is, right? Not as polar as bent, but it's still pretty polar. That one would be called a non-polar molecule, and that's different than a polar bond, right? A polar molecule versus a polar bond. If I look at this particular molecule, let's go back to CH4. We were talking about CH4. And if we look at CH4 as being a non-polar molecule, it's non-polar because there's no non-bonded pairs of electrons sticking up. However, if I look at the bond between hydrogen and carbon, on the periodic table, carbon and hydrogen are pretty darn far apart from each other on the periodic table. So that bond is very polar. It's an unequal sharing of the electrons between the carbon and the hydrogen. And in fact, carbon is hogging those electrons more. So that pair of electrons that exists between carbon and hydrogen, the electrons spend more time around carbon and a little bit of time around hydrogen. Then they'll spend more time around carbon and then a little bit of time around hydrogen. And that's why this bond is very polar. But the molecule itself is non-polar, right? Now, this molecule, we're going to use this to represent NH3, right? Here's NH3. This bond is polar, but then the molecule is polar also because it's got this negative area of electrons sticking out. And if we go one more to water, this bond is polar, but the molecule is also polar, right? So you can have polar bonds and polar molecules, but you can also have polar bonds that give you non-polar molecules, and that would be a really good topic for an essay question on this particular unit. Just saying. All right, so there's linear. A good example is CO2. Trigonal planar. If you take trigonal planar electron geometry and then you have a non-bonded pair, all of a sudden trigonal planar becomes bent, which makes sense, right? Because you've still got 3 electron domains around the central atom, but now one of those electron domains is a non-bonded pair, which pushes the other 2 down and creates a bent electron geometry. What would be the angle between the atoms in this particular molecule up here, which is BF3? What would be the angle between the B's? 120. All right, here, what would you predict the angles between the O's to be? Well, not 90, but it would certainly probably be less than 120, right? Because that non-bonded electron pair would push it down a little bit more. I don't know exactly what the number is, but I would say it's probably a smidge less than 120. All right, here's this idea of non-bonding pairs and bond angle that is illustrated here with the tetrahedral, like this is CH4, NH3, H2O. See those non-bonding pairs of electrons? They smoosh that angle between the hydrogens in the component atoms. And that's because if you look at, here's a non-bonding pair of electrons. It's a very symmetrical looking cloud of electrons. Here's a non-bonding pair, right? See how it's a much bigger lobe of repulsion and it sort of shares it a little bit better here. And we already talked about tetrahedral. Now let's talk about some of the more complex molecules. Trigonal bipyramidal. Good example here is PCl5. We look at PCl5 in terms of its Lewis structure. Let's do PCl5 Lewis structure. All right, so we have PCl5. Phosphorus has 5 valence electrons. Each coin has 7. 7 times 5 is 35, so I have a total of 40. So I got P in the middle, and this is an atom that already is going to be violating the octet rule. What do I mean by it's violating the octet rule? has more than 8 electrons around it. And the central atom can do that. When we get to these more complex molecules, the central atom can violate the octet rule. All right, 2, 4, 6, 8, 10. I subtract 10 electrons from my total, I've got 30 left. I need 6, 12, 18, 24, 30, right? So I put my valence electrons in for PCl5. And I'm really not too concerned about the valence electrons on those other than the fact that I'm achieving my octet. If I look at PCl5, it's going to look like this, right? All right, this is what they call trigonal bipyramidal, right? Here's the trigonal part around the outside. So if I'm looking at just the bond angle between these atoms, what's the bond angle between these atoms? 120, all right? Here's the bipyramidal, right? There's a pyramid on the top and a pyramid on the bottom. What do you suppose is the bond angle here in these? That's a 90-degree angle. So this molecule has 120 versus 90-degree angles between the component atoms, and that's important to know. All right, so when you make something that is not have all 5 of those bonded, like say, for example, you have a non-bonded pair of electrons, that non-bonded pair comes from one of the trigonal part of the trigonal planar. So if I look at this molecule, when I change it and I have a non-bonded pair, I'm going to take one of those atoms off from the trigonal part, all right? And the example here that they give us in the textbook on molecular geometries, it is SF4. So when you create SF4, and you can practice that one on your own, practice SF4, you'll see that it's got also 5 electron domains area around the central atom, but one of those is non-bonded. So now the electron geometry of this is called what? What's the electron geometry? The electron geometry is trigonal pyramidal, right? Or trigonal bipyramidal, right? All right, the molecular geometry is, we call it what? Seesaw, right? And that makes sense, and it's called seesaw, right? Because if you make the molecule and you look at it, it's supposed to look like a seesaw, like it did in elementary school, right? All right, if you change this, and now instead of having 1, 2, 3, 4, 5 areas of electron domains that are all bonded, now you take another one off. Now this one, the electron geometry of this molecule is still trigonal bipyramidal, right? But now the molecular geometry, when I've got 3 bonded pairs and 2 non-bonded pairs, what do we call this one? T-shaped, which makes total sense, right? That it would be called T-shaped. Now, if we think about polarity, remember polarity of the molecule? Let's compare polarity of these molecules. All right, when it's like this, is it going to be polar? No, because now, is this a bond? Is this bond polar? That's the first thing we have to look at. Is that a polar bond? It's a polar bond between phosphorus and chlorine, right? Phosphorus and chlorine, they're pretty close to each other, but the bond is still going to be polar, it's still going to be unequally shared. Who's going to be more greedy for those electrons, phosphorus or chlorine? Chlorine, but it's going to be pulling out symmetrically in all directions. So even though that bond is polar, the molecule itself is non-polar because it's very, very symmetrical, right? Doesn't it look symmetrical? All right, take one of these off. Now I've got the electron geometry that's still trigonal bipyramidal, but now it's seesaw. Is this going to be polar? It surely is, because look, I got a big lobe of electron repulsion at the top of this molecule. All right, I go down to the next one. I take off another atom, and now I have T-shaped. Do you suppose that's going to be polar? That's definitely going to be really polar, right? This one is sort of polar. This one is really polar, because now I've got 2 areas of electrons here that are negatively charged, and all these are slightly positive. So, see, when it's polar, I got one area of the molecule that is negative, and on this side, the molecule is positive. Now, finally, when I go to the last one, I take this one. Now, it's still trigonal bipyramidal electron geometry, but now what do we call this molecular geometry? Linear. Now, is this going to be polar? No, because even though you got this negative area all the way around the outside, it's still a very symmetrical molecule. Once again, you can have a polar bond, but the molecule itself is all very nonpolar, specifically on this one. Now, usually, if the electron and molecular geometry are different, then it's usually a polar molecule, but there are exceptions like this one, where the electron and molecular geometry, so this one, the electron geometry would be what? Trigonal bipyramidal, right, still, but then what would the molecular geometry be? Linear. So the electron and molecular geometry are different in this one, but this molecule is nonpolar because it's very symmetrical. And finally, the last one, if we look at the last molecular geometry and how that can change, that's octahedral, where we've got, once again, I don't know why they call this octahedral. I personally would have called it square bipyramidal. That's what I would have called it, but I didn't name these things. I'm just using the names that somebody else invented, right? So if we look at this particular one, it starts out looking like this critter right here, right? So we've got 4 areas of electron domains and then 1 on each side. So what are the bond angles around all of this molecule? All are 90 degrees, right? All the bond angles are 90 degrees around this molecule. Is this going to, now if this is our electron geometry, it's called octahedral. Now when you lose atoms in this one and you start to have non-bonded pairs, it turns out that instead of you losing it around the outside like you did with the trigonal bipyramidal, you lose them on the ends. So if you look at this molecule, if I'm going to lose a pair of electrons, I'm going to lose one on this end first. All right. So now my electron geometry is still octahedral, but now what do I call my molecular geometry? Square, right? Square pyramidal, right? So it's supposed to be a pyramid looking like that, or I guess you could look at it like that. So there's the square pyramidal. Now in this one, is this going to be a polar molecule or a non-polar molecule? That's going to be pretty polar because we've got a big area of negatively charged electrons on one end of the molecule, and this end is going to be slightly positive. Now, in this kind of molecule, when you lose another one and you have an area of non-bonded electrons, it looks like this. So now my electron geometry is still octahedral, but now what do I call my molecular geometry? Square planar. Now this one has non-bonded pairs, but is this going to be a polar molecule or a non-polar molecule? It's going to be very non-polar because even though I got a big negative charge here and a big negative charge here, they balance each other out and they're symmetrical. Right? Makes sense? See how easy this molecular geometry stuff is when we spend 2.5 hours on it in lab? Right? Easy peasy. All right, let's make sure. Oh, larger molecules. You may have to look at what is the electron geometry of this carbon. What's the electron geometry here? Tetrahedral. What's the molecular geometry? Tetrahedral. All right, and this is a question on your exam. There'll be one just like this. What is the electron geometry around the second carbon? Trigonal planar. All right, that's the electron and molecular geometry, right? What is the electron geometry around this oxygen? Tetrahedral. What's the molecular geometry? Bent. What's the angle between the atoms in carbon 1? 109.5. What's the angle between the oxygens in this one? 120. What's the angle between the carbon and the hydrogen in this one? Like 105, something like that, 105. It smooshes it down even more, right? Okay, you need to know those. That's pretty much it. We're done.